I'll give you the exams at the end of the class. I have them graded. So let's learn something. So an announcement. I will have very limited office hours this week. Okay? So if you have questions, so please use email for questions. If there is something that we won't be able to resolve via email, we can set up some kind of a virtual classroom and we'll chat. Okay? So, you know, I just have some issues going on this week. Wife is out of town, I'm on the baby duty, and it's weird. I might be late as well for class. Miracle that I made it here on time. So, if necessary, I might be here tomorrow, so just, email me. Are you there? I'm like, yeah or no. So, whatever. We'll have a homework for due Friday. So, nothing due on Wednesday. And I'll publish it. It's almost done. It's just a bunch of graphs. Okay? No, it's not up. Yeah, it's almost there. I just need to basically make it live. Um, all right, so we're in section 6.5 right now. We started talking trigonometric graphs. And so what we know so far, we got the sine graph. So this is what we ended up with. So if you remember, we had some point 0, pi. Well, let me do this pi over 2. Pi, 3 pi over 2, 2 pi. So the graph looked like that. And we also agree that this is a periodic function, so it keeps going with a period of 2 pi. And it was bounded on the y-axis by 1 and -1. Right? So just by looking at this graph, what is the domain? All real numbers, right? There's nice, pretty continuous thing. So domain is all real numbers. How about the range? -1 to 1, including the -1 to 1. Is that okay? Now, what about the cosine? So we already got the graph for the cosine x. So we also looked at the similar points, pi over 2, pi, 3 pi over 2, 2 pi. So it looked like that. So domain and the range, same stuff. Do you agree with that? Domain will be all real numbers. Ranges from -1 to 1. Okay. So, all right, so let's get the other two. Let's do tangent, cotangent, and eventually we're going to do secant and cosecant. But let's do graph of tangent. And I'm going to use the unit circle again to produce the graph of tangent. So let's make our unit circle. So what are our points there? Is that fair? Okay. So now if you recall, what is the definition of tangent? What is tangent? Oh, we don't know that yet, but yes. Opposite over adjacent, but in terms of the points on the unit circle, it's y over x, right? And as we agreed, sine is y, x is cosine. So yes, so technically tangent is also sine over cosine. But tangent x based on the unit circle is y over x. Okay? So it has a division in it, but there's a very special division. It's division of two coordinates. So we have to be careful, because that x that's in the denominator, that thing equals 0 sometimes. Do you agree with that? Can x equal 0? What? Nothing? I mean, it can equal 0 in the unit circle, but we wouldn't want it to be 0 in the fraction, right? So let's just see, well, when does x equal 0? For what values of theta? 90 degrees, so pi over 2. And then if I keep going, that's x equals 0 again. So 270, so pi over 2, 3 pi over 2, right? And, you know, negative pi over 2 and negative 3 pi over 2. So basically what we get odd multiples of pi over 2. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Yeah, so we'll have asymptotes, vertical asymptotes at those points, because that's division by 0. So I can actually go ahead and put all those odd multiples. So this is pi over 2, this is pi, this is 3 pi over 2. So odd multiples of pi over 2. So let me label a whole bunch of points. So we'll have vertical asymptotes at odd multiples of 3 pi over 2. Odd multiples of pi over 2. So pi over 2, 3 pi over 2, pi over 2, and so forth. Okay? Okay, so those are the asymptotes. How about the x-intercepts? So the x-intercepts is when the numerator equals 0. Right? So since tangent is y over x, the graph of tangent will cross the x-axis when y equals 0. But y on the unit circle. This is This is the hard part to distinguish between the y on the unit circle and the y on the graph. Those are different y's. Okay? So when is the y on the unit circle equal 0? 0, pi, 2 pi, 3 pi. So it's multiples of pi. Right? So we will have x-intercepts at the multiples of pi. Okay? So now, see what happens in the first quadrant. First of all, we know that tangent is positive in the first quadrant. Remember that? We talked about that last time. Tangents are positive in the first and the third quadrant. Right? Well, if you look at the xy plane, this interval right here represents the first quadrant on the unit circle, from 0 to pi over 2. Figure that? So the tangent will be above the x-axis on that interval. Now, what will happen to the values of tangent as theta increases from 0 to pi over 2? So as you close to 0, the values of y are small, right? Close to 0, while the values of x are close to 1. So these values are going to be very small. The ratios of y to x at these points are going to be very small. But as you travel along and you get closer to this point, what's happening? The values of y get close to 1, while the values of x get close to 0. So your divisor is very small. So the ratio is going to get really big, right? If you start dividing by something that's close to 0, the actual quotient is going to be infinite. So you will get this kind of effect. It will shoot out to infinity like that. It will have that asymptotic behavior. Okay? Now, as we travel along the unit circle, now we're in the second quadrant. The value of tangent is negative in the second quadrant, right? And look what happens. We have the same effect. As we start our travel along the unit circle, the values of x are very small. So the ratios are going to be really, really large, but large negative. So it will start on the bottom, will come down to pi. And as you're moving in the third quadrant, everything will become positive again. So if we just keep doing it, it will just look like that. So this is how we produce the tangent curve. Okay. So just by looking at the graph, what is the domain of this function? What is the domain of the tangent function? Sure. Yes. Because the distance between each asymptote is exactly pi. So I can say that the domain is all x's such that x does not equal to pi over 2 plus pi k. Yes. So, or odd multiples of pi over 2. What about the range? From negative to infinity. Everything is covered on the y-axis, so the range is all real numbers. Is that okay? Now, we already talked about the period of these functions, and we mentioned this last time, that just by looking at, and now even by looking at the graph, you can see that the period of the sine and cosine is 2 pi. It repeats itself in intervals of 2 pi, so I can say period here is 2 pi, and period there is 2 pi. But if I move to the tangent curve, and again, we mentioned that before, but just by looking at the graph, can you just say what the period of the tangent graph is? Pi, right? It repeats itself in the interval of length pi, right? So the period is pi. Okay? Okay, so this is the graph of tangent. Let's do cotangent. So now remember, cotangent is x over y. And I can again use the unit circle to produce the values, or I can think about the whole co-function business. Because remember how tangent and cotangent are co-functions, right? What does that mean? So those are the complementary angles, but the tangent and cotangent will be equal for complementary angles, right? So remember this co-function identity, that tangent x equals cotangent of pi over 2 minus x, or vice versa. Right? So what that means, I can use the graph transformations. All that means I have to reflect the graph of tangent over the y-axis, that's the negative sign, and then shift it by pi over 2. So if you think about this, can you visualize what's going to happen? If I shift this by pi over 2, so my intercepts will become where the asymptotes used to be, right? And my asymptotes will be where the x-intercepts used to be. You hear that? But then you also reflect it, so the graph will actually do something like that. So when you flip it, it'll go away. We'll make a new one. But does that make sense? You shift it by pi over 2, and then you flip it over the y, or vice versa. But you will have the asymptotes at multiples of pi, so 0, pi over 2, pi, 3 pi over 2, 2 pi, so it will have asymptotes at just multiples of pi. It will have the x-intercepts at the odd multiples of pi, but it will also do this reflective thing. Okay? And again, we're staying consistent. If you think about this, cotangent has the same signs as tangent. So tangent is positive in the first quadrant. So this interval represents the first quadrant. So cotangent is positive in the first quadrant. This is the second quadrant on the unit circle. Cotangent is negative. This is the third quadrant, positive. Fourth quadrant, negative. So are you comfortable with me flipping between the unit circle and regular XY plane? It's a little weird, but eh. So, what is the domain of this function? Sure, multiples of pi. So you can say all x is such that x is not equal to pi k. What about the range of this function? What? All real numbers? What about the period? Period is pi. Okay? So questions on how we produce this graph? No questions? Okay. Let's do cosecant. So cosecant is what? That's r over y, right, on the unit circle? Or it's the reciprocal of sine curve. So in other words, cosecant x is 1 over sine x. Those are reciprocals, okay? So I can actually use the graph of the sine curve to construct the graph of the cosecant curve. So let me do a sine curve really fast. So if I'm trying to graph the reciprocal of this function, so that means I'm dividing by the values of these functions, am I going to be in trouble at any points? Are there any asymptotes? That's what I'm trying to say. So cosecant will be defined for all real numbers? Right, except for sine of x equals 0, because if sine equals 0, 1 over sine is going to be undefined, right? So we're actually going to have asymptotes where the sine crosses the x-axis. And this is actually how you're going to be graphing the cosecant functions in the future, because I can give you something weird, don't write this down, but if I give you something like, 2 cosecant of x plus 1 minus 3, something like that. Don't write this down. But in order to graph this function, you will first graph the sine function, and then you start interpreting the asymptotes and so forth. So I'm actually showing you how we're going to be doing this stuff in the future. Okay. So now will cosecant have any x-intercepts? What do you think? So will 1 over sine x ever equal 0? That's what I'm asking. No, because the numerator is 1. In order for a fraction to equal 0, the numerator has to be 0, right? But at the same time, what is the range of sine x? Remember that part? What is the range of sine x? Yeah, between -1 and 1. So if you think about this, since the denominator never gets bigger than 1, right? Denominator is never bigger than 1. The ratio is always going to be greater than 1, right? If you have 1 over less than 1, you'll get bigger than 1. Do you like that notation? Well, think about this. Numerator is 1, denominator is less than 1. So the ratio is going to be bigger than 1, right? The only times when the ratio equals 1 is actually at these points. That's where the cosecant and the sine will actually meet. Because at this point, sine equals 1, so cosecant equals 1. Because those are reciprocals. At this point, right here, sine equals -1. So reciprocal of -1 is -1. Agree with that? At this point, the value of sine is -1. The reciprocal of that is -1. Right? But the rest values will be greater. So actually the graph of cosecant is something like this. It will have that asymptotic behavior. So it will actually do this. So those red parabola-looking thingies, that's the graph of the cosecant. It has the asymptotes at multiples of pi, and then just basically goes out. It always greater or equal to 1 or less than or equal to -1. So this is how you'll be producing the graphs of cosecant in the future. You'll first grab the sine curve, then put the asymptotes where the x-intercepts are, and then just kind of invert everything. So to graph a cosecant, you're first going to have to graph sine. So what's the domain of this function? Go ahead. Right, so all x's except for pi k. Right? How about the range? That's right, including the ones, right? So from -infinity to -1, including -1, union from 1 to infinity. So it has a gap in between -1 and 1. So basically it's the opposite of the range of the sine curve, right? The sine is just from -1 to 1. This is everything else. But they do meet at those points. They do meet -1 and 1. What about the period? So now again, remember, this is the pi. This is the length pi. So if the period was pi, it would have to be the same all the way across. So what's the period? 2 pi. So it's the same as the sine. How's that? So in order to do the secant curve, we'll do the same thing. We're first going to sketch the cosine x, and then we're going to find the asymptotes and kind of do the very similar process. So graph of secant x. So again, we'll start with the cosine curve. So the cosine does something like that. So that means that the secant will have asymptotes at pi over 2, 3 pi over 2, negative pi over 2, and so forth. Okay, so when the cosine crosses the x-axis, that's where the secant has its asymptotes, but the rest will be the same. just look like this. So what is the domain? Mm-hmm. Actually, no, we've been doing this wrong. Pi over 2k. Yeah, we've been doing this wrong. It's odd multiple, so it's 2k plus 1. Because again, because if you just let k to be anything, yeah, we have to go fix that. Because like, if k is anything, if k is 1, you get pi over 2, but if k is 2, you get just pi. So we have to be more careful. Odd multiples of pi over 2. So let's go back and fix those. We have to fix it on... Oh, wait. Before, because you said it differently before. You said it pi over 2 plus pi k, right? That's how you said it before. That's okay. Yeah, that's fine. Or pi over 2 times, but that's not pi over 2k. Okay. Yeah, you were right before. Now, what is the range? Range is the same as cosecant from negative infinity to negative 1, including negative 1, union from 1 to infinity. And the period is 2 pi. Okay? So these are the basic 6 trig functions and their graphs. So now we're going to have fun with them. So this is the next section, the section 6.6. So the transformations. So we're just going to apply all of our algebraic knowledge about how to transform the graphs to the basic trig functions. So let's talk about the basic variations. So I'm just going to do sines and cosines first. So I'm going to draw a few, I'm just going to write a few functions. Let's say y equals 5 sine of half x, or y equals negative 3 cosine of 1/2 x minus 3. Or just like y equals 2 sine of 4x plus 2. So let's just talk about this. In the first example, we do know the shape of the sine curve. We do know what that looks like, right? What is the big 5 on the outside going to do to the graph of sine x? Stretch it which way? Vertical. So it's just going to multiply everything by 5, right? So if you think about this, if your original sine curve was going between -1 and 1, when you multiply everything by 5, we're going from -5 to 5, right? So that increases the, well, I'm not going to use the proper word yet, but it increases the, yes, the amplitude. It increases the size of the sine curve in the vertical direction. So remember how we agreed before. If you mess with the function, the changes happen vertically, right? So 5 stretches the graph vertically. What about 1/2 on the inside? What is that going to do? Hmm? No. So remember what we talked about before during week 1. If you mess with the variable, it changes things horizontally. But the horizontal changes are always counterintuitive. Because the intuition tells you if I'm multiplying by 1/2, I'm making things smaller, so it should shrink. Well, it should be the opposite of whatever your intuition tells you. It's going to make it bigger. It's actually going to double everything, okay? So it'll actually stretch well, not vertically, horizontally. So it changes the period of the function. If you think about this, if you take the sine curve and you stretch it horizontally or you shrink it horizontally, the period will change. Do you agree with that? So those things will actually affect period, but we still apply our prior knowledge to doing all of those graphs. How about the second one? What will -3 up front do to the graph of the cosine? We know the cosine graph. What's -3 up front is going to do to the graph of the cosine? Right, so the negative sign flips it over the x-axis. 3 will stretch it. So it will still go from -3 to 3, but it'll be reflected over the x-axis. I mean, we'll do all those graphs later. But at least we understand that the same rules still apply. What is all that junk on the inside? 1/2 x minus 3. What's going to happen? It's going to affect the horizontal, right? It's going to affect the x-axis in which way? It's going to stretch and it's going to move, right? The 1/2 is going to do the stretch. The minus the number is going to move it which way? To the right. By how much? I don't know about that. I have to be very careful. Because of that 1/2 messes us up. We're actually going to be thinking about this function as cosine of 1/2 and then x minus 6, like that. Right? Because this is the same as 1/2 x minus 3. So what is subtracted from x? 6. It's actually going to shift by 6 and then stretch. See that? Because the 3 is not subtracted from x. 3 is subtracted from 1/2 x. So it will flip, stretch vertically, stretch horizontally, and will also shift to the right. And it will change the period. Since we're stretching things horizontally, what do you think the period will be? I mean, are we that good? Can you predict the period when you do 1/2 x? So when it's just x, the period is 2 pi. You're doing 1/2 x, you're stretching it. But you're stretching it. Is it going to make the period bigger or smaller? Bigger. And you have 1/2, so you're going to stretch it by 2. So what will happen to the period? 4 pi. Yeah. 2 pi, you double that, becomes 4 pi. While in the next one, the 2 up front will stretch everything vertically. Let's do 1/2 up front. 1/2 up front. What is that going to do? Shrink it vertically. So it's going to be bouncing between -1 and 1. I mean, -1/2 and +1/2 on the y-axis. What will 4 on the inside do? It's 4 times x. shrink it horizontally by a factor of 4. So if the original period was 2 pi, now you're making everything 4 times as condensed. So 2 pi period will become pi over 2. So it's just 2 pi divided out by 4. So it'll give you pi over 2. I mean, we'll make all that stuff official, but at least we can predict what's going to happen. So if you shrink it horizontally, the frequency of your graph increases. So the period becomes much shorter. And what about that plus 2 just hanging on the outside? But it's plus 2 on the outside, up to, right? Because we're messing with the whole function. We're not messing with the variable. So everything's going to go up 2. So if you think about this, the 1/2 made your graph bands between -1/2 and +1/2. But you add 2, it's going to go from 3/2 to 5/2. So that's where the graph is going to occur. Okay? So we're going to put it all in a nice perspective and make certain rules, and we're going to learn how to graph those things, and maybe I'll show you a few shortcuts. But we'll have some joy out of that, hopefully. So what we're trying to graph y equals, so I'm just making sure I'm using the same letters as your book. So these guys. So you can have a constant on the outside, you can have a few constants inside, and another constant on the outside. So y equals a sine of bx minus c plus d, and y equals a cosine of bx minus c plus d. Okay? So let's do the easy one first. The easy transformation is the plus d part. Because what is the plus d going to do? Just go up or go down, depending on d, right? If d is positive, everything's going to go up. If d is negative, everything is going to go down, right? So I'm going to start with an example. So just playing with d. So for example, if I want to sketch y equals sine x plus 2. So it's 2 added to the whole function. So every y value gets 2 added to it. So think about this. The sine, let me see, do I have anything? Nice lines. Oh, just this one. So this original sine is, no, that's not. So the original sine is this, right? So it's bounded by -1 and +1, right? Well, now everything gets shifted by 2. So my new range is going to be from +1 to +3, right? That's between these two values, the sine curve is going to be bouncing. My new y-intercept is going to be that point, the 2, right? So everything is going to go up 2 units, so I can actually go ahead, just kind of keep it in between these two lines and just try to mimic the graph below, right? Or, I can just totally do this, right? But that's what's happening. So everything just gets shifted 2 units up. Yeah, I can just do all that. But we're just going 2 units up. Is that okay? Pretty straightforward. So this would be what if I do this example? Y equals cosine x minus 3. So what's going to happen? Yeah, it's going to move down 3. So basically, we're going to do the same thing. So the original cosine did this. This is the original cosine curve. So now its new range, since we're subtracting 3, 1 becomes -2, and that's also the the y-intercept, right? And it's going to go all the way down to -4. So the cosine is going to be in between these two lines, right? So I can just do this. Well, actually, it won't work. Oh, it will work. So I can just drop it down there. So there we go. Okay, so this is the cosine x minus 3. So that's the easy part. This is the easiest one to play with if you add a constant to the outside. The second easiest thing to play with is to play with a. The stretching. That's actually simple. The messes on the inside is going to be a whole different story. But that a, that part is simple. So let's play with a. So let's say I want to do y equals 2 sine x. So this is the original sine curve. So the original sine curve between -1 and 1. Now if you double everything, the new curve will go from -2 to 2. But from what you remember from algebra, when you do a vertical stretch, do your x-intercepts change? The x-intercepts stay the same. Because what is the value of the y value? The x-intercept is 0. You double 0, that's still 0. So everything is going to look like that, right? All the y values just doubled. So this would be the graph. Is that okay? Any questions on this? Straightforward? How about y equals -3/2 cosine x plus 2? Try that one. So we're combining two transformations. I'm giving you the value of a and the value of d. So I have a and d together in there. So we're getting anything good? Good enough? What does that mean? So I'm going to start with the cosine curve. So this is my cosine curve. You know, this is pi over 2. This is 3 pi over 2. So again, the original cosine is between 1 and -1. What will -3/2 up front do to the graph? Stretch it vertically, and what else? And flip it. So it will now go between -3/2 and +3/2. Flipping it vertically, will that change the x-intercepts? No. So now it looks like this. Right? And +2, what is that going to do? Go up 2. So now it's going to be bounced between +1/2 and you add 2. What do you get? 3/2 plus 2. 7 halves, right? So then you just shift the graph to kind of that. It'll actually go, it won't go through 0, go through like through 1 half, right? The new, the y-intercept is at 1 half now. So it'll actually stay, it will not, it's not going to touch the x-axis. So what is the range of this function? Well, the range. Yeah, so it's from half to 7 halves, right? But yeah, the domain is all real numbers. So this will tell us how large the swing of the sine curve or the cosine curve is. So this constant up front will tell us that is the amplitude. We call it the amplitude. So or cosine. So in equations, y equals a sine of bx plus c. Now we're doing minus c, yes. So minus c here. And the value of absolute value of A is the amplitude. The reason why we look at the absolute value of A because the sign of A does not affect how large the swing is. It just flips the graph, right? But it does not affect the range of that function. So when I ask you, here's this first example, what is the amplitude of that function? 1, right? You look at the constant in front of the function, it's 1, so the amplitude is 1. Same thing for this graph. For the second one, the amplitude here is 1. But as I move along to this example, when it says 2 sine x, now the amplitude is 2, right? You just look at the constant in front of the function. How about the last example we did? What is the amplitude of that last function? 3 halves. You ignore the negative sign, you just take the absolute value. Because again, it will tell me the swing and goes up 3 halves, down 3 halves, right? This is the amplitude. It goes 3 halves, 3 halves, 3 halves, 3 halves. Doesn't matter if you flip it or not, it will not affect the range. Is that okay? All right. So any questions on what the amplitude is? Scroll down. Yeah. So let's play with B. So for example, if I give you y equals sine of 2x. So what we agreed, if you multiply the variable by constant bigger than 1, it will shrink the graph of the function horizontally. So if we think about this, the original intercepts were pi, 2 pi, negative pi, negative 2 pi, so the graph of the original sine curve was this. Right? So now if I shrink everything horizontally, what are my new x-intercepts going to be? Yeah. So now it's pi over 2. Now pi. 3 pi over 2. All those become my intercepts, right? So it will actually look like this. Everything shrunk by half. Did that affect our range? I mean, looked like it did, but it shouldn't have, right? The range stayed between -1 and 1. Now, all it did, it changed the period of this function, and the period now, as you see, the period now is just pi, okay? So what that number does, it affects the period, or sometimes we call it frequency. Of the function. So in general, the period, so in equations, y equals a sine of bx minus c plus d, and y equals a cosine of bx minus c plus d, the period is the absolute value of 2 pi over b. Again, the reason why we're using the absolute value, if b is negative, it will not affect the frequency of the graph. It will flip the graph, but it will not affect how it stretches. So in order to find the period of those new graphs, you just take the original period and you divide it by b. Okay? Side note, if we were playing with tangents, you would take the period of tangent and divide it by b. So it'll be just pi over b. Does that make sense? So now if I just give you a function, for example, y equals 3 cosine of negative x over 2 plus 2, can you tell me the amplitude of this function? 3, right? What about the period of this function? 4 pi. So you take 2 pi and you divide it by a half. So that being x at 4 pi. So we have a function that's stretched horizontally. Now period is 4 pi. It's stretched vertically by 3. It is flipped over the y-axis, right? And it also shifted 2 units up, right? Let's see if we can sketch the graph of this thing. Well, for the cosine, actually, it doesn't. Yeah, with sine, something will change. Yeah, but you're absolutely right. With the cosine, it's redundant to put a negative on the inside. Okay, we'll mention some of those fancy details later, but it will actually should help you to understand what type of function cosine is. If you go back to algebraic classification of cosine functions. So we're going to go from -3 to +3, right? And the period will change. So now the period, if I do the original graph of the cosine, so it's something like this, right? This is the original cosine. So this was pi. This is 2 pi, right? So this is pi over 2. This is not pi. This is 3 pi over 2. What am I doing? This is 2 pi. I'm just silly. This is pi. Yeah, that's better. Sorry. So now I'm just doing two things. I'm doing 3.5. So what will that do? It will stretch it, but it will also change, right? So x-intercepts are now I have to be careful. What will happen if I stretch it? So yeah, something like that, right? Yeah, so that's kind of ugly. But that's the first period of that cosine. Now, if I flip it over the y-axis, is anything going to change? If that negative sign flips it over the y-axis, so nothing changes. So the only thing that's left to do is put it up 2. I should have gone a little further down to -3 in here. This is awful. So if I try to shift all of this up 2 units, that's not going to. Missed all that mess. All my extra lines. Oh my God, that's a lot of extra lines. You getting the idea? So it's, oops. It still goes up to -1 over here. Now my new x-intercepts are very fancy. I'm not going to be able to find them yet. But they're not trivial. They're not anything in terms of like pi, so we won't be able to do them. I mean, we might, but this is the ideas. Is that okay? Okay, good. So now we have a little bit of time left. I'm going to give you